Hello, this is your homework helper for section 4.3. In this section, we're talking about intervals of increasing or decreasing of functions and also the first derivative test. So here, let's jump right in. The reason I picked this one is because it's got the trig functions in it, and that throws people off sometimes, but mostly because of this interval. They restrict the interval here. And when we do the test here, for increasing or decreasing, that's going to play an important role, and people mess that up sometimes. So let's jump right in. First, we've got to find these critical numbers, right? We're looking for where the function's going up, where the function's going down, so we've got to know where it may change from increasing to decreasing, and that's where the critical numbers are. So when we do the derivative here, we're going to do the power rule on this. We bring the 2 down. 2 times 2 is 4. Leave the cosine x the same, but then with chain rule, multiply by the derivative of cosine, right? Which is negative sine. And then minus 2. The derivative of cosine is negative sine, so we're going to write, I'll just change the sign here to positive and write sine x, right? So the idea is that we've got to set this equal to 0, right? We've got to find our critical number. So where is that function going to be equal to 0? We also want to know where this function's undefined, right? Where the derivative is undefined. But cosine x and sine x have a domain of all real numbers, so we can put any x value in there and get a value out. So there's no places where this derivative is undefined. But where is it equal to 0? Well, we're going to factor out, let's see, what do they have in common? A 2 and a sine x, yes? And then what's left over? Well, what we've got here is a negative 2 cosine x and then a plus 1. Okay, so we're looking for our zeros. Where is this one equal to 0? Well, sine x is equal to 0. Keep in mind, we're on our unit circle, and we're only going around the circle once from 0 to 2 pi, right? Don't include 0 and 2 pi, because those are the endpoints of our interval, and they're not included. So we only want the ones in between those two values. So pi is the only place where sine x is going to be equal to 0, right? So x is equal to pi. That's the only solution from that one. Now from this one, if that's equal to 0, then cosine x is equal to 1/2. And cosine x is equal to 1/2, right? I'm just pulling out my unit circle memory here, right? It's equal to pi over 3, and it's also equal to 1/2 when x is 5 pi over 3. Okay? So those are our three critical numbers. We've got pi, pi over 3, 5 pi over 3, not necessarily in that order. So the way I like to do these is I make a number line, right? And I make a little note here to say, okay, this is representative of my first derivative, right? F prime of x. And then I put all these numbers on the number line. Putting them in order, pi over 3 is the smallest. Sorry, my phone said it's almost out of battery, so I better hurry. I've got 5 pi over 3 here. This is 5 pi over 3. Oh, sorry, I'm going too fast now because I'm worried about my phone running out of batteries. Pi should be in between the two, right? And then this one should be 5 pi over 3. Good. Now what I'm going to do is check in between those regions. What's important is that you don't check something outside the domain that we are interested in, right? We're going from 0 to 2 pi. So I'm going to put a little note here that says 0 is the low endpoint and 2 pi is the upper endpoint, because I don't want to check numbers outside there, right? 0 would be a critical number if it was included in the domain I'm interested in. So it might change from increasing or decreasing out there. So if I check a number like negative pi over 3 or negative pi over 6 or something like that, then it might throw off what this interval does, because it's a different interval of increasing or decreasing, because 0 is a critical number. So just make sure you stay inside the domain when you're checking in between these regions. Okay, so let's go ahead and check. So I want to check, let's see, something in between 0 and pi over 3. Let's check pi over 6. And keep in mind, you don't have to know exactly what the derivative is equal to at pi over 6. You just have to know if it's positive or negative. All I want to know is if this interval is an increasing interval or a decreasing interval here, right? So all I care about is if this is negative or positive. So I don't have to actually find the number. I just have to find what the sign would be, right? So here's 2, right? I'm going to evaluate the derivative here at this step. It's just easier than all this mess up here. So 2 sine x, okay, sine of pi over 6 is 1/2. Right? And then negative 2 cosine of pi over 6 is square root of 3 over 2. Right? And then plus 1. And I'm just trying to decide if that's positive or negative. At pi over 6, is this derivative positive or negative? Well, these two are going to multiply to a positive. This all actually comes out to be a negative, right? The 2's cancel. You get a negative square root of 3, which is, the magnitude's bigger than 1. So when you add all that together, you get a negative number. right? So this is a negative times a positive, which is definitely a negative. The derivative being negative in here means it's going to be derivative all the way through because the sign of the derivative doesn't change anywhere else on this interval because I know my only critical numbers are the ones that I've listed here. So I know it's got to be decreasing on that entire interval. I'm just going to do the same thing for the other three intervals. Picking a number between pi over 3 and pi, I think the easiest thing to pick would be pi over 2 because it makes, it makes these sine and cosine make some easy numbers to find. So I'm going to put 2 here, and sine of pi over 2 is 1, and cosine of pi over 2 is 0. And again, I don't care what it's equal to. This one's easy. It's equal to 2. But all I care about is this is positive times a positive times a positive. So whole thing's positive. And I'm increasing on that interval. Just a note, the book does this a little bit differently. They do it with a table instead of with a number line, but the end result is the same. I just think the number line's easier to see what's going on. Again, I'm going to pick a number in between these two. Maybe 3 pi over 2 is the easiest. 2. Sine of 3 pi over 2 is negative 1, and cosine of 3 pi over 2 is 0. You can see why I'm picking the numbers I'm picking. It makes the calculations easier. That also helps. This is going to be positive because of the 0, right? So it's just positive 1. This is negative. This is positive, so it's going to be less than 0. And this interval is going to be a decreasing interval. And then f prime of, let's pick a number in between these two, maybe 11 pi over 6. 2. Sine of 11 pi over 6 is negative 1/2. And cosine of 11 pi over 6. Cosine of 11 pi over 6 is square root of 3 over 2. This is going to be negative. This is going to be negative, right? Just like before, I'm kind of cheating here, right? 11 pi over 6 and pi over 6 are very similar. There's just the only difference is this negative 1/2 of sine, right? So this was negative before. It's going to be negative again, right? This is positive. This is negative. So it's a negative times a positive, which is definitely positive. So it's increasing on that interval, right? So the end result of all that is that I know, right, going back to the original question, identify the open intervals where the function is increasing or decreasing, right? So now I know it's going to be increasing from pi over 3 to pi, and also from 5 pi over 3 to 2 pi. WebAssign doesn't make you use interval notation. I put the union symbol in between there just to show it's increasing on both of these intervals. I believe in WebAssign you just have a multiple choice of different intervals to pick, and it's just you want to pick those two. Where is this function decreasing? Same idea, just pick the other two intervals, right? 0 to pi over 3. Union with decreasing, let's see, pi to 5 pi over 3. Okay, so there's a good example with some trig to get you through that one. And that's the other thing is that we could use this to identify the relative maximum and minimum, right? I now know that at x equals pi over 3, I have a relative minimum because it was decreasing before and increasing after. And also at 5 pi over 3, I have a relative minimum for the same reason. And at pi, I have a relative maximum because it's increasing before that and decreasing after that. That's kind of why I like this picture better than doing it with the table. I can really see sort of what's going on there. I don't know what the y values are, right? In order to find what the y values, I have to put these values back into the original function. But I can tell the x values where the relative minima and maxima occur, all right? This one I picked because it throws people off because people think that this graph is actually the function that the question is referring to, f. But there's this little prime here, right? It says this is the graph of f prime, right? This is the graph of the derivative, in other words. It's not the graph of the original function. So they want you to use this graph of the derivative to identify the critical numbers of the original function, okay? So remember, I'm going to kind of follow the same path I did before. The first thing we have to know is we have to find those critical numbers. And they kind of give that to you. They say identify the critical numbers, right? Okay, so what are the critical numbers? Now, the critical numbers occur where the derivative is 0 or where the derivative is undefined. This derivative graphed on the interval that I have here, it's defined everywhere, right? There's no skips or jumps, so this derivative is defined everywhere. Where is this derivative equal to 0? Well, it's at the x-intercepts, right? At negative 5, it looks like there's a critical number. At 2, it looks like, and at 6, right? So I have three critical numbers again, -5, 2, and 6. And I sort of want to do the same thing I did before in the last problem. Here's my derivative, and you know, this is just a sketch of the domain. It's really quick, inaccurate. I'm not drawing these to scale or anything, right? I just want to represent all the intervals that I have. And what I can see here is that I'm not even going to plug in x values. I can see it from the graph of the derivative, right? This derivative is positive to the left of x equals -5, right? Because it's above the x-axis. So I know the original function is increasing on that interval because the derivative is positive. On this interval between -5 and 2, it's also above the x-axis. So the derivative values are positive for all the x values on that interval. The derivative values are negative in between 2 and 6, so it'd be decreasing there, and positive after x equals 6, right? So I'm sort of doing the same thing I did in the last problem. I'm just doing it with the graph of the derivative instead of plugging numbers into the derivative. So what we've got here is before -5, the function's increasing. After -5, the function's increasing again. So that's that's not an extrema, right? Because it's increasing before and increasing after. So I would say -5 is neither a maximum or a minimum, right? It's neither one at that value. And at 2, let's see, we're increasing before and decreasing after. So that means at 2, there's a relative maximum. And at 6, it's decreasing before and increasing after. So it's a relative minimum. I hope that helps. That one really confuses people sometimes because they think this is the graph of the function, not the graph of the derivative. It's a little tricky. It's kind of even hard to see that. I wish they would have said in this problem, use the graph of the derivative of the function instead of doing this little notation, because people often miss that little prime there. But I hope those two help. And email me if you have any questions, and keep up the good work.